Hello, you may have heard of divide and conquer. In probability theory, you could solve very difficult problems. As a matter of fact, this is why probability theory is so important, because you could decompose a very complex problem into smaller pieces and then solve it. This is called total probability, because the total probability can be divided into pieces, separate problems, solve them, and then assemble the total together. So in this section, which we call it total probability, we see a very simple theorem, and which is derived from conditional probability and then the additivity property of the probability measure. So this theorem says that if you have a number of mutually exclusive and collectively exhaustive events, it doesn't need to be finite, but it should be countable. So you have AI such that these AIs are disjoint. So the set, this is your L, the sample, the possible outcomes, and then this is A1, a portion of it, this is A2, and etc. AN. So, so the last one. So first of all, A1 and A2, AI and AJ, their intersection is empty. So no points appear more than once in one of these sets. And second thing is that union of these guys, so A1 union A2, etc., union AN, which I abbreviately show that as union over I AI. So these creates the whole sample space. So they're all possible outcomes. So no point is outside of all of them. So every point appears only in one of them. In that case, if you have any other event, let's say event B, which is, let's say, suppose that this is B, okay? So this is event B. So this set B can be decomposed into, let's say, this, I call it this B1. Then you have another portion of B, which is B2. So these partition, this set of mutually exclusive collectively events is called a partition. So this partition divides B into, so B becomes equal to B1 union B2, etc. union Bn. So what happens is that the intersection of any of these two guys, so B1 intersection B2, is empty. Okay? So 2 by 2, they are disjoint, and their union is equal to B. So I have two properties. First of all, B is equal to union of BI, I equal 1 to n, okay, and then they're disjoint. So therefore, in this circumstance, I could write probability of B. I could say that because of their disjoints, probability of B is equal to summation of probability of BI's. Okay, but remember that BI itself is intersection of B and AI. Okay. So what I concluded is that this guy is equal to summation over I equal 1 to n, and this guy is probability of B intersection with AI. Okay. Now here you can use the definition of the conditional probability and get these theorem proven. So the proof is very easy. So you divide B. You could say that B, the proof, if you want to write it formally, B is equal to B intersection with L, and B, because they are mutually exclusive, this L is equal to the union of these guys. Using De Morgan theorem, you could say that intersection of union, you could change the order easily. And because now these guys are disjoint, so this is equal to probability of sum of union of probability of union of disjoint set is equal to sum of their properties, because their intersection is empty. And therefore this will become is equal to sum of these guys, and this one you can use the property of conditional probability, and the proof is complete. So this theorem is called total probability theorem. That means that if you ever want to calculate probability of B, you could calculate it in pieces separately under different circumstances. Define 2, 3, 4, 5 different circumstances, calculate probability of D under each circumstances, and then add the calculated probability together when you put different weights. Okay, so this is called, and this is the key to solving many problems. So let us have one example. For instance, consider a binary communication channel. A binary communication channel, your input could be 0, 1, and your output also could be 0, 1. If you transmit 0, with some probability you will have a correct reception. If you transmit 1, you can get correct reception, or you could have errors. So if you want to calculate probability of overall correct reception in terms of these probabilities that are written here, this is called the transition probabilities, or the characteristic of the channel. So in this question is that what is the probability of correct reception of data? So, or what is the probability that A, the transmitted signal, is equal to the received signal? So I could say that probability of A given B, so I could put different conditions. So my conditions, so I make a partition. So my partition is that I define A1 as event that the transmitted signal A is 1, and A2 is A is 0. Okay, so we see that these two are disjoint, and their union is the whole sample space. So because your transmitted signal is either 0 or 1. So I could say that this event, given this condition, times probability of this condition plus probability of the same event given the second condition times the weight of the second condition. So if you put the numbers there, you get this equation. So total probability theorem can solve this problem very easily.